Greetings and salutations, magical chemists. Today we're going to look at manipulating reactions and see what effect that has on the equilibrium constant K. First, let's talk about changing stoichiometric coefficients. Well, if you multiply the coefficients in an equation by a given factor, you actually have to raise the equilibrium constant to that power to get the equilibrium constant for your new reaction. Let's take a look at why that is. Well, in an equilibrium constant expression, your stoichiometric coefficients are in fact exponents. So if you change the coefficients, you're changing the exponents in your equilibrium constant expression. So when we take that reaction and divide all the coefficients by 2, notice that changed the exponents. It actually went ahead and changed the exponents by that factor. It divided the exponents by 2. I'm saying exponents a lot because people often confuse this with Hess's law. Remember, thermochemistry, you could look at enthalpy in delta H, multiply a reaction, multiply delta H by 2. It was the same thing. This is not the same thing. Equilibrium constants are a little bit trickier. So you can also reverse the reaction. In Hess's law, we just flip the sign on delta H. Nope, not here. Because, of course, we're writing our equilibrium constant expression as products over reactants, if you flip the products of reactants, you have to flip the fraction. You have to take the reciprocal. Notice, by the way, there's a standard notation when you're given an initial reaction with an equilibrium constant K. We say that the new K for the manipulated reaction, we call it K prime. Okay, just like with Hess's law, you can add equations together, but this time, if you add 2 or more chemical equations, you will have to multiply their respective equilibrium constants. Now, mathematically, all these things are pretty straightforward, but I will give you a fair warning. These are very commonly missed problems because people treat it like enthalpy, like Hess's law, but it's not. K is different. All right, let's go ahead and try a few of these. Okay, in each of these examples down below, we're starting with the same given equation, the Haber process, which takes nitrogen gas and hydrogen gas and turns it into ammonia. And it has this particular equilibrium constant at 127 degrees Celsius. Well, now they're saying that's fine, but what would the value of the equilibrium constant at the same temperature be if we had this reaction? Well, hopefully you can see that in this case, we just flipped the reaction, which means we have to take the reciprocal of the K value we started with. So our new K value, or K prime, is just 1 over our old K value. And hopefully it makes sense that since this reaction was spontaneous in the forward direction, when we reverse the reaction, it now has a small K value and it is no longer spontaneous. All right, take a moment. I want you to try pots B and C all on your own. Gasp! So take a moment to try those, and when you're ready to check, unpause the video. In part B, we took the initial reaction, and we basically multiplied all the coefficients by 1/2, or divided them by 2. So we need to raise our initial equilibrium constant to the 1/2 power, which means take the square root. Okay. The last reaction was more fun because we flipped this reaction and multiplied it by 3. But that's okay. We can do 2 things simultaneously. Well, because we reversed the reaction, we have to take the reciprocal. But because we multiplied it by 3, we also have to raise it to the power of 3. But that's it. Then just plug and solve. All right. Let's go ahead and move forward. And we're going to spend a little more quality time with the reaction quotient. Q. Q is written just like K, and it's the ratio of products to reactants, but you calculate Q at any condition. So Q is what you calculate when you need to know the answer to the question, is the system at equilibrium? And the answer could be yes, and it could be no. We can compare the value of Q to the value of K to see where are we currently and where are we trying to go. And that allows us to predict which direction the reaction will have to shift to reach equilibrium. Remember the trick, if you write it in alpha order, then the inequality sign can become an arrow pointing the direction the reaction will shift. If K is greater than Q, that means that you don't have enough products yet to be at equilibrium, so you are going to shift right and make more products. Now, if they're about the same, then the system is at equilibrium. And if K is less than Q, that means you currently have too many products, you're not at equilibrium, so you have to shift back towards reactants. Okay, let's look at Q in terms of that beautiful free energy graph. You can use the value of Q to compare to K and determine the thermodynamic favorability of a reaction system from the point it's currently at. Notice if the forward reaction is favored, if you're basically anywhere over here, under current conditions, you are not in a stable place. You do not have the correct ratio of products to reactants. So spontaneously, some reactants are going to turn into products. So if you have a Q value less than K, or K greater than Q, that means your delta G value is negative. It is a spontaneous reaction under those conditions. But if it's the other way around, under these conditions, the reverse reaction is favored. You need to make more reactants, which means you're not going to spontaneously make products, which means it's thermodynamically unfavorable. Of course, when you're actually at equilibrium, the system is at its lowest point for Gibbs free energy, so delta G is 0. It's not changing its free energy because it's already at the most stable place. I realize I've scribbled all over this graph, but hopefully that at least kind of makes sense. Well, since we know a little bit about kinetics, we can actually use Q versus K and draw some information about the rate of the forward reaction relative to the rate of the reverse reaction. Because of course, when you're at equilibrium, the definition of equilibrium is that the rate of the forward reaction is exactly equal to the rate of the reverse reaction. But if you're not at equilibrium, and equilibrium is being approached from the left, means you have too many reactants and you need to make products. Well, the rate of the forward reaction is going to start really high, but it's going to slow down as you make more and more products. The rate of the reverse reaction is going to start low, but it's going to speed up as you make more and more products that can then turn around and go back to reactants. And of course, the rates stop changing once the forward reaction has decreased so much and the reverse reaction has increased so much that they're equal. And you can probably imagine it's exactly backwards if you're starting with too many products. In that case, the rate of the forward reaction will start low, but it'll get bigger. And the reverse reaction will start high, but it'll get smaller until they have both reached the same rate. Now, what's interesting, and you're speaking of kinetics and how fast things happen, well, the time required to reach equilibrium has nothing to do with the equilibrium constant K. Of course, it does depend on another K, lowercase k, the rate constant K, because that's not confusing at all. It's important to note that regardless of where you start on that graph, regardless of your initial ratio of products to reactants, at a specific temperature, the reaction is going to reach equilibrium at the same place, at the same ratio of products to reactants. That lowest free energy point is going to be the same at a constant temperature. Okay, in summary, I made a little table that kind of tries to encapsulate all that information together. Basically, what'll happen if K is greater than Q, if they're about the same, or if K is less than Q. But remember, if you're not at equilibrium, you're approaching equilibrium. So things are going to change until that point of stability is reached. Okay, that whole K versus K thing, thermodynamics versus kinetics, can be really confusing. So I wanted to take a moment to look at that because capital K, the equilibrium constant K, has to do with thermodynamics. We spend a lot of time in thermodynamics talking about delta G and Gibbs free energy, but remember delta G and the capital K equilibrium constant are related by the negative Ratlink equation. Kinetics is our lowercase k, the rate constant K, and that's talking about how quickly things will happen. And this is, of course, determined by the activation energy of a given reaction mechanism. So let's break that down a little bit. There are actually some things you can determine about the about the rate using the value of the equilibrium constant, basically about lowercase k by using capital K. You can compare the relative rates of forward and reverse reactions by comparing K and Q. However, you can't tell anything absolutely about the rate of a reaction. If it's a slow reaction, a fast reaction, a first order, second order, whatevs, you absolutely cannot compare that information by comparing equilibrium constant values. This is a constant source of AP trickery, so be on the lookout for this. They'll try to trick you into drawing a conclusion about the speed of a reaction by using the equilibrium constants, but you can't do it. Okay, let's move away from kinetics for the moment and try a little bit of tasty math looking at K versus Q and predicting the direction of shift. What's fun is that now, not only do we have a KP with the ratio of partial pressures, you can have a QP. I think there's a QP doll, which makes that kind of creepy, but. So you can use QP to predict the direction the reaction is going to shift if you are given current conditions. Luckily, this is exactly like calculating normal Q with the concentration ratio and comparing it to K. But watch out for the way you write it. We're using parentheses, not square brackets. So, if you're given current conditions and you want to know which way a reaction is going to shift, you have to start by calculating the current ratio, Q. Okay, well, the current ratio at these conditions of products to reactants is 16. But hopefully you see they actually told you your equilibrium constant, Kp. I mean, they have to tell you it, otherwise you don't have anything to compare to. So, that's only like 0.3. Well, let's compare these two. Clearly, K is less than Q. Under current conditions, you have too many products. You are not at equilibrium. Well, what's the reaction going to do? It's going to shift. In this case, it's going to shift left to decrease the partial pressure of products and reach equilibrium. Okay, there's another practice problem here that I want you to try and check before we finish the video. So please pause the video and try this delicious problem now. The second problem is giving you, once again, the equilibrium constant and asking you to predict the direction of shift. But it's in terms of concentrations. So this time we're looking at Kc and Qc. To be honest, though, I usually don't write the C, I just call it Q. Okay, once we write out our QC expression and solve, we get a pretty dang tiny value. But remember, it doesn't matter how small Q is. It only matters what Q is relative to K. So let's check. Well, in this case, K is a tiny value too, but K is still bigger than Q. So the reaction this time doesn't have enough products. It's going to shift right to make more products and achieve equilibrium. And that's it. So there you have it. Thank you for playing with the glories of chemistry.